Hello, welcome to my presentation video on earthing schemes in low voltage distribution. My name is Martin Lavachka, and in this video I'm going to talk about earthing connections, the definition of standardized earthing schemes, the characteristics of TT, TN, and IT systems, their selection criteria, choice of earthing method and implementation, and installation and measurements of earth electrodes. Earthing connections. National and international standards clearly define the various elements of earthing connections. The following terms are commonly used in industry and literature. Earth electrode, a conductor or group of conductors in intimate contact with and providing an electrical connection with Earth. Earth, the conductive mass of the Earth, whose electric potential at any point is conventionally taken as zero. Electrically independent Earth electrodes. Earth electrodes located at such a distance from one another that the maximum current likely to flow through one of them does not significantly affect the potential of the others. Earth electrode resistance. The contact resistance of an earth electrode with the earth. Earthing conductor. A protective conductor connecting the main earthing terminal of an installation to an earth electrode or other means of earthing. Exposed conductive part. A conductive part of the equipment that can be touched and which is not a live part but which may become live under faulty conditions. Protective conductor. A conductor used for some measures of protection against electric shock and intended for connecting together exposed conductive parts, extraneous conductive parts, the main earthing terminal, earth electrodes, and the earthed point of the source or an artificial neutral. Extraneous conductive part. A conductive part liable to introduce a potential, generally earth potential, and not forming part of the electrical installation. For example, non-insulated floors or walls, metal framework of buildings, and metal conduits and pipework for water, gas, heating, compressed air, etc., and metal materials associated with them. Bonding conductor, a protective conductor providing equipotential bonding, and main earthing terminal, the terminal or bar provided for the connection of protective conductors, including equipotential bonding conductors and conductors for functional earthing, if any, to the means of earthing. Connections. The main equipotential bonding system. The bonding is carried out by protective conductors, and the aim is to ensure that in the event of an incoming extraneous conductor being raised to some potential due to a fault external to the building, no difference of potential can occur between extraneous conductive parts within an installation. The bonding must be effected as close as possible to the points of entry into the building and be connected to the main earthing terminal. However, connections to the earth of metallic sheets of communication cables require the authorization of the owners of the cables. Supplementary equipotential connections. These connections are intended to connect all exposed conductive parts and all extraneous conductive parts simultaneously accessible when current conditions for protection have not been met. For example, the original bonding conductors present an acceptable high resistance. Connection of exposed conductive parts to the earth electrodes. The connection is made by protective conductors with the object of providing a low resistance path for fault currents flowing to earth. Effective connection of all accessible metal fixtures and all exposed conductive parts of electrical appliances and equipment is essential for effective protection against electric shocks. In figure E2, you can see a list of exposed conductive parts and extraneous conductive parts. Definition of standardized earthing schemes. The choice of these methods governs the measures necessary for protection against indirect contact hazards. The earthing system qualifies three original independent choices made by the designer of an electrical distribution system or installation. The type of connection of the electrical system and the exposed parts to the earth electrodes. A separate protective conductor or protective conductor and neutral conductor being a single conductor. The use of earth fault protection of overcurrent protective switchgear, which clears only relatively high fault currents, or the use of additional relays able to detect and clear small insulation fault currents to earth. In practice, these choices have been grouped and standardized. Each of these choices provides standardized earthing systems with three advantages and drawbacks. Connection of the exposed conductive parts of the equipment and of the neutral conductor to PE conductor results in equipotentiality and lower overvoltages but increases earth fault currents. A separate protective conductor is costly even if it has a small cross-sectional area, but it is much more unlikely to be polluted by voltage drops and harmonics, etc., than a neutral conductor is. Leakage currents are also avoided in extraneous conductive parts. Installation of residual current protective relays or insulation monitoring devices are much more sensitive and permits in many circumstances to clear faults before heavy damage occurs. The protection offered is in addition independent, concerning changes in an existing installation. TT system. One point at the supply source is connected directly to earth. All exposed and extraneous conductive parts are connected to a separate earth electrode at the installation. This electrode may or may not be electrically independent of the source electrode. The two zones of influence may overlap without affecting the operation of protective devices. TN systems. The source is earth like in TT system. In the installation, all exposed and extraneous conductive parts are connected to the neutral conductor. TNC system. The neutral conductor is also used as a protective conductor and it is referred to as a PEN conductor. This system is not permitted for conductors of less than 10 mm squared or for portable equipment. The TNC system requires an effective equipotential environment within the installation with dispersed earth electrodes spaced as regularly as possible, since the PEN conductor is both the neutral conductor and at the same time carries phase imbalance currents as well as third order harmonic currents and their multiples. The PEN conductor must be therefore be connected to several earth electrodes in the installation. Caution: in the TNC system, the protective conductor function has priority over the neutral function. In particular, a PEN conductor must always be connected to the earthing terminal of a load, and a jumper is used to connect this terminal to the neutral terminal. The TNS system is obligatory for circuits with cross-sectional areas less than 10 mm squared for portable equipment. The protective conductor and the neutral conductor are separate. On underground cable systems, where lead sheeted cable exists, the protective conductor is generally the lead sheet. The use of separate PE and N conductors is obligatory for circuits with cross-sectional areas less than 10 mm squared for portable equipment. TNCS system. The TNC and TNS systems can be used in the same installation. In the TNCS system, the TNC system must never be used downstream of the TNS system, since any accidental interruption in the neutral on the upstream part would lead to an interruption in the protective conductor in the downstream part and therefore a danger. In the figure, you can see a connection of the PEN conductor in the TNC system. IT systems. In an IT system with isolated neutral, no intentional connection is made between the neutral point of the supply source and the earth. Exposed and extraneous conductive parts of the installation are connected to the earth electrode. In practice, all circuits have a leakage impedance to earth, since no insulation is perfect. In parallel with this resistive leakage path, there is the distributed capacitive current path. The two paths together constituting the normal leakage impedance to earth. In a low voltage 3-phase 3-wire system, 1 km of cable will have a leakage impedance due to C1, C2, C3, and R1, R2, and R3 equivalent to a neutral earth impedance of 3000 to 4000 ohms, without counting the filtering capacitances of the electronic devices. In an IT system with impedance earth neutral, an impedance ZS is connected permanently between the neutral point of the transformer LV winding and the earth. All exposed and extraneous conductive parts are connected to an earth electrode. The reason for this form of power source earthing are to fix the potential of a small network with respect to earth and to reduce the level of overvoltages, such as transmitted surges from the MV windings, static charges, etc., with respect to earth. It has, however, the effect of slightly increasing the first fault current level. Characteristics of TT, TN, and IT systems. In TT system, if the exposed conductive parts are earthed at several points, an RCD must be installed for each set of circuits connected to a given earth electrode. The main characteristics of TT systems are simplest solution to design and install, used in installations supplied directly by the public low voltage distribution network. Does not require continuous monitoring during operation, and protection is ensured by special devices, the RCD, which also prevents the risk of fire when they are set to less or equal to 500 milliamps. Each insulation fault results in an interruption in the supply of power. However, the outgauge is limited to the Foley circuit by installing the RCDs in series or in parallel. Loads or parts of the installation that, during normal operation, cause high leakage currents require special measures to avoid noisy stripping. For example, supply the loads with separation transformer or use specific RCDs. TN system. Generally speaking, the TN system requires the installation of earth electrodes at regular intervals throughout the installation, requires that the initial check on effective stripping for the first insulation faults be carried out by calculations during the design stage, followed by mandatory measurements to confirm stripping during commissioning. Requires that any modification or extension be designed and carried out by a qualified electrician, may result in the case of insulation faults in greater damage to the windings of rotating machines, and may on premises with a risk of fire represent a greater danger due to the higher fault currents. In addition, the TNC system at first glance would appear to be less expensive, requires the use of fixed and rigid conductors, and is forbidden in premises with a risk of fire and for computer equipment. In addition, the TNS system may be used even with flexible conductors and small conduits, and due to the separation of the neutral and the protection conductor, it provides a clean PE. The main characteristics of IT systems are solution offering the best continuity of service during operation, indication of the first insulation fault followed by mandatory location and clearing, ensures systematic prevention of supply outages, and generally used in installations supplied by a private NV-LV or LV-LV transformer, and requires maintenance personnel for monitoring and operation. Requires a high level of insulation in the network. The check on effective tripping for two simultaneous faults must be carried out by calculations during the design stage, followed by mandatory measurement during commissioning on each group of interconnected exposed conductive parts, and protection of the neutral conductor must be ensured. Selection criteria. In terms of protection of persons, the three system earthing arrangements are equivalent if all installation and operation rules are correctly followed. Consequently, selection does not depend on safety criteria. It is by combining all requirements in terms of regulation, continuity of service, operating conditions, and the types of network and loads that is possible to determine the best system. Selection is determined by, above all, the applicable regulations, which in some cases impose certain types of system earthing arrangements. Secondly, the decision of the owner if the supply is via a private NV-LV transformer or the owner has a private energy source. If the owner effectively has a choice, the decision on the system earthing arrangements is taken following discussions with the network designer. The discussions must cover the operating requirements and the operating conditions and the particular characteristics of the network and the loads. Choice of earthing method and implementation. Division of source. This technique concerns the use of several transformers instead of employing one high-rated unit. In this way, a load that is a source of network disturbances can be supplied by its own transformer. The quality and continuity of supply to the whole installation are thereby improved and the cost of switchgear is reduced. The cost effectiveness of separate transformers must be determined on a case-by-case basis. Network islands. The creation of galvanically separate islands by means of LV-LV transformers makes it possible to optimize the choice of earthing methods to meet specific requirements. Conclusion. The optimization of the performance of the whole installation governs the choice of earthing system, including initial investments and future operational expenditures hard to assess that can arise from insufficient reliability, quality of equipment, safety, continuity of service, etc. In an ideal structure would comprise normal power supply sources, local reserve power supply sources, and the appropriate earthing arrangements. Installation and measurements of earth electrodes. The quality of an earth electrode depends essentially on two factors: installation method and type of soil. Buried ring. This solution is strongly recommended, particularly in the case of a new building. The electrode should be buried around the perimeter of the excavation made for the foundations. The bare conductor must be in intimate contact with the soil. At least 4 vertically arranged conductors from the electrode should be provided for the installation connections, and where possible, any reinforcing rods in concrete work should be connected to the electrode. The conductor forming the earth electrode, particularly when it is laid in an excavation for foundations, must be in the earth at least 50 centimeters below the hardcore or aggregate base for the concrete foundation. Neither the electrode nor the vertical rising conductors to the ground floor should ever be in contact with the foundation concrete. For existing buildings, the electrode conductor should be buried around the outside wall of the premises to a depth of at least 1 meter. As a general rule, all vertical connections from an electrode to the above ground level should be insulated for the nominal low LV voltage. Earthing rods. Vertically driven earthing rods are often used for existing buildings and for improving existing earth electrodes. The rods may be copper or copper-clad steel. The latter are generally 1 or 2 meters long and provided with screwed ends and sockets to reach considerable depths if necessary. And galvanized steel pipe less than or equal to 25 mm in diameter, or rod less than or equal to 5 mm diameter, less than or equal to 2 meters long in each case. It is often necessary to use more than one rod, in which case the spacing between them should exceed the depth to which they are driven by a factor of 2 to 3. The total resistance is then equal to the resistance of one rod, divided by the number of rods in question. Vertical plates are rectangular plates, each side of which must be uh, equal to or greater than 0.5 meters, are commonly used as earth electrodes, being buried in a vertical plane such that the center of the plate is at least 1 meter below the surface of the soil. The plates may be copper of 2 millimeters of thickness or galvanized steel of 3 millimeter thickness. In this figure, you can see resistivity for different types of soil and average resistivity values for an approximate sizing of earth electrode. Measurement and constancy of the resistance between an earth electrode and the earth. The resistance of the electrode-earth interface rarely remains constant. Among the principal factors affecting this resistance are humidity of the soil, frost, aging, and oxidation. Measurement of the earth electrode resistance. There must always be removable links that allow the earth electrode to be isolated from the installation so that, so that periodic tests of the earthing resistance can be carried out. To make such tests, two auxiliary electrodes are required, each consisting of a vertically driven rod. Ammeter method and use of direct reading earthing resistance ohmmeter. This is the end of this presentation. Thanks for watching.